Where are you listening from? And what time is it there? It is a small question, soft as a pillow, and yet it contains an ocean. Say it aloud in your mind, and you will notice two things at once: a point on a dial and a feeling in your chest. The dial says one thing, your chest may say another. That gentle mismatch is the very place I want to walk with you tonight, slowly, kindly, as we follow the many faces of time, from the way your minutes stretch and fold inside you to the vast, faint movement of the universe itself. Imagine for a moment sitting by a window. You can hear a clock somewhere in the house, a low, steady tick. Outside, the light is changing, long and honeyed, or perhaps it is that grey, muted light that tells you the day is closing. Notice your breath. Notice the tick. These two measures of rhythm, the inner and the outer, will be our companions. We will meet an old river called Newton's time, a trampoline called Relativity, a mattress with a bowling ball pressed into it, and later a fragile photograph album of the universe. But for now, let us begin with the place where time first touches us every day, the mind. 10 minutes in a waiting room can weigh like an anchor. 10 minutes in a hobby can feel as if someone has tucked those minutes into the inner lining of your memory and stitched them tight. The same seconds, different weight. This is not a trick of clocks, it is the shape of attention. When you are alert and curious, when your senses are filled with novelty, the mind lays down rich, dense memories. Later, those minutes seem long when you look back. When you are bored or anxious, when attention is thin and scattered, those minutes are less stitched. They pass with a hollow sound. A psychologist named Mihai Csikszentmihalyi, there's a name worth pronouncing slowly, called one of those sweet states flow. In flow, action and awareness slip into one another. You are playing, painting, typing, or skiing, and there is a quiet tunnel through which you move. Time does odd things there. It can contract, as if the minutes themselves were folded and tucked away. Hours pass with the softness of a blink. Yet when you remember that time later, it is full-bodied and dense. That density is the mind's way of saying, something happened here. The world altered me. Try a tiny experiment with your attention now. Think of the last time you waited for a kettle to boil. Now think of the last time you were absorbed in a book and realized on turning a page that the kettle had been whistling for some time. Which felt longer? The waiting, almost certainly. Why? Because when the mind is anchored to the expectation of a sound, to the watchful tapping of impatience, each second gathers weight. When the mind is elsewhere, the seconds slide past like pebbles under a stream. Memory acts like a larder for time. Childhood summers, full of firsts and small ignitions, are heavy with memory because the mind was busy collecting details, faces, scents, the precise angle of sunlight. As we grow older, the steady repetition of days leaves fewer fresh bookmarks, so time, as recalled, can seem to accelerate. Novelty stretches time outward, routine tightens it back into a neat spool. There is a tender consolation in this. Time is not only an outside measurement, it is partly a craft we practice with our attention. If you want a breath of different time, you do not need an expensive change of scene. You need surprising moments, tiny shifts in attention, small rituals that create new memory anchors. The mind will respond. It is not commandment, it is an invitation. Notice that. Breathe. And if you like this gentle voyage through time, a little click of like and a quiet subscribe helps others find this restful corner. From the inner clock we move at a very slow pace to the first human attempts to name the hours. Look up. The sky is a slow clock, patient and indifferent. Long before anyone made gears or glass faces, people read time from shadows and the arc of the sun. An obelisk planted in light casts a shadow that moves like a slow hand across a stone face. Sundials do not measure minutes as our wristwatches do, but they give rhythm, morning work, midday rest, evening prayer. The shadow is a living sketch of the day. Water clocks or clepsydras kept another kind of time. Water trickled, and as it filled or emptied a vessel, it measured duration. Imagine the soft hiss of water, a sound that somehow makes waiting kinder. These early clocks were not for obsession with precision. They were practical, domestic and communal, for planting, for markets, for prayers. They taught us that time could be shared, that a community could agree on the shape of the day. There are cultures that folded time into the very fabric of their cosmology. Stone monuments aligned with solstices show that human clocks were once made from the motion of the heavens themselves. The sky was not an abstract background, it was a giant, reliable instrument. Seasons became maps for sowing and harvest, rituals became calendars. In those first measures, time felt like something outside us that we learnt to read. There is a charm to these humble instruments. Picture a village square, a sundial stone catching light, children chasing each other while an elder checks the shadow before calling the hour. It is domestic, tactile, human. The sky tells time in a way that makes us feel small and held at once. That double mood of belonging and of wonder is the same feeling that cosmology later aims for on a very large scale. The practice of reading the sky slowly evolved into the art of building things that could keep time when the sky was hidden. The leap from shadows and drips to tuned metal and balance wheels is a story of human patience and curiosity. For a long time, clocks were large and communal, church tower clocks, bells across a valley. Then came smaller machines, the verge escapement, a crude but functional way to control the release of energy and produce a steady beat. Imagine little teeth on wheels giving and accepting impulses, like a careful conversation between cogs. Christian Huygens, a Dutch gentleman with a contemplative brow, noticed that a swinging pendulum makes a slow, predictable motion. He borrowed that motion into clocks, and suddenly timekeeping became steadier than it had ever been. The pendulum is such a lovely domestic metaphor, a swing moving back and forth, each travel marking a small, sure count. The world's noisy variables are tamed by this simple motion, at least in the protected world of a clock. Then there was John Harrison, who married patience to craft in a way that belonged on a small wooden table lit by a lamp. Harrison wanted a clock that would keep time at sea. In the 18th century, ships navigated by the stars and by the drummer of chance. A reliable timepiece could fix longitude and save lives. Harrison built chronometers that coped with humidity, temperature, and the constant motion of a rolling deck. They were delicate wonders, small islands of stability in an ocean of motion. He taught us that precision could be portable, that timekeepers could travel. The march towards accuracy did not end with brass and pendulums. A new material, quartz, enters the story in the 20th century. Quartz crystals, when gently nudged, vibrate at a very regular frequency. In a small piece of glass, millions of tiny swings keep their own time, steadier than many mechanical parts. Quartz clocks made accurate timekeeping cheap and widespread. Watches on wrists, clocks in microwaves, little reliable heartbeats of civilization. And finally, there are atomic clocks, which belong a little to the realm of marvel. At the heart of such a clock is an atom, often cesium, that oscillates between energy states. The definition of the second, as current international agreement says, is based on the frequency of that oscillation, 9,192,631,770 cycles per second. It is a number that reads oddly when you say it out loud, but it describes a kind of steadiness at the tiny quantum scale. To call it beautiful is not to be poetic, it is simply to notice that a human measure, a second, can be grounded in the very regular behavior of atoms. Atomic clocks have practical effects that are delightfully prosaic. The global positioning system that guides a phone's map relies on dozens of satellites carrying such clocks. If those clocks drift by even a tiny fraction of a second, positioning errors accumulate into kilometers. Engineers compensate for time's slipperiness. They program circular corrections that include even slight relativistic effects. The physics and the everyday meet on a smooth, usable surface. If you picture the history of clocks in domestic terms, it is a story of turning something spread across the sky into something you can hold in your hand. From an obelisk's shadow to a tiny chip inside a phone, the same human impulse threads to anchor action, to coordinate, to live with one another in predictable ways. Yet even with all that accuracy, there is a deeper question. What exactly is time itself? Is it a thing that flows, a river that carries us, or is it just a way of noting change? Two philosophers of the 17th century argued this question in different clothes. Isaac Newton, whom many of us meet as the man of falling apples and gravity, imagined time as absolute. For Newton, time was like a great river, steady and uniform, passing regardless of what happens in it. It is a soothing image, a calm, measured flow that provides a background against which events unfold. It lets you imagine an objective now that is the same everywhere. Gottfried Wilhelm Leibniz, on the other hand, proposed a different picture. For Leibniz, time is not a separate thing that exists on its own. Time, instead, is a web of relations between events. If nothing changes, there is no time to speak of. The world is a sequence of differences. Time, on this view, is the catalogue of how things affect one another. It is less a river and more a ledger of relationships. Both pictures are useful. They are lenses through which we frame questions. Newton's river lets us calculate motion in a convenient scaffold. Leibniz's relational view nudges us to ask, where does time come from if the universe had no change? Both are partial truths, models that help us get to the next line of the story. And then, in the 20th century, the story deepened in a way that asked us to reconcile the very idea of now. Albert Einstein came along not to soothe, but to unsettle gently. He asked what happens to time when you move near the speed of light, or when you stand beside a very massive object. His insight was to bind time and space into a single fabric, space-time. Picture a trampoline stretched taut. A heavy object, a bowling ball, placed on the trampoline makes a dip. Small balls rolling nearby will curve inward. Paths that seemed straight are gently bent. That dip is an image for how mass warps space-time. Clock ticks are sensitive to that warp. First, a quiet note about simultaneity. In everyday life, we imagine a shared now, that you and I can point at a single slice of the universe and call it the present. Special relativity tells us that simultaneity depends on the motions of observers. Two events that are simultaneous for you might not be simultaneous for someone moving relative to you. It is a delicate idea, not because it is mystical, but because it asks us to loosen a comfortable habit, the assumption of a universal now. Time dilation is another gentle surprise. If you travel fast, not at bus speeds, but at speeds approaching that of light, your clock ticks more slowly compared with a stationary clock. A commonly used yarn to help feel this is the twin thought experiment. One twin stays at home, the other sets off in a high-speed ship and returns younger than their sibling. In real life, we have confirmed the effect with flying atomic clocks. Planes carrying precise timepieces return with clocks that have measured passing at a slightly different rate than their ground-based twins. The numbers are small for the speeds we can practically reach, but consistent and real. The universe keeps time, and it keeps it differently depending on motion and gravity. Gravity itself also tugs on time. The deeper you sit in a gravity well, close to a planet for instance, the slower your clock will tick relative to someone farther away. The bowling ball on a trampoline metaphor gives the right gentle intuition. The presence of mass creates a curvature that affects the paths of both light and time. Experiments place precise clocks at different altitudes and show that the higher clock runs faster than the lower one by a minuscule but measurable amount. Those tiny differences matter for GPS satellites high above the Earth. Engineers must account both for the satellite's speed and the weaker gravity at altitude. Without those corrections, your map would begin to wander. Einstein's insights knit together the cosmic and the domestic. The same equations that describe bending light near a star also explain why a clock on a satellite and a clock on your bedside table disagree if you do not correct for spacetime's indentations. In a gentle sense, the universe refuses to be perfectly uniform. It offers us different experiences of duration depending on circumstance. There is a certain humility in that discovery. The older image of a single universal river loses its authority. Time is local in an important way. Your now is meaningful in your frame. But if time is flexible, we might ask, why do we seem to experience one direction of time? Why is the past fixed, the future open? Why do glasses fall and splinter rather than their shards assembling themselves on the floor? It is a question that nudges us toward entropy, to the second law of thermodynamics. But before we step into that slightly darker, very cosmological territory, allow the image of the trampoline and the bowling ball to sit for a moment. Feel its curves. Consider the joy of possession the universe gives us, to trace a shadow on a sundial, to hold a pendulum's slow swing, to know that the second you notice is both your own and part of a larger foreign rhythm. There is comfort in that. There is room for wonder. We will soon wander into the idea that the universe itself had a special beginning, an initial state of remarkable order, and that the growth of disorder ever since may be the root of the arrow of time. We will consider glass shattering, scrambled eggs, and the cosmological puzzles that make physicists sit up late and sip cold tea. But not yet. For now, keep your attention on two things: the low, steady tick somewhere in your house, and the airy fact that time behaves differently when motion or mass come into play. Let those facts dwell like small stones in a pocket. If you raise your eyes from your own hands to the stars, you can see how the same issues magnify. A rotating neutron star bends space and time differently from a loaf of bread. Light from ancient galaxies is stretched. The universe's expansion shapes photons on their long journey. Our century's clocks, those tiny, precise atoms humming at billions of oscillations per second, are the instrument by which we have come to confirm these disturbances. We measure, and the universe answers in faint, exact ways. And there is another, quieter thread that runs parallel to these measurements. While physicists tune instruments and adjust for relativistic corrections, another field, one intimate to you and me, studies how organisms keep time. The body has its own clocks, nested and layered, like nested boxes. A central pacemaker in the brain, called the suprachiasmatic nucleus, or SCN, keeps circadian time, aligning our cycle of sleep and wake with the day-night rhythm. Hormones like melatonin rise and fall. Some people are morning people, some are not. Jet lag is a small, insistently human example of what it feels like when an internal clock bumps for a while against a new external rhythm. I mention this now because the story of time is not just mathematical, it is ecological and biological. Cosmic rhythms and biological rhythms do not need to be the same to speak to one another. They can exist in parallel, sometimes in harmony, sometimes not. You can feel very much at rest inside your circadian comfort and still know, with a strange kind of gratitude, that the universe's clock is under no obligation to match you. There are experiments that measure time across these domains. Flights around the world have carried atomic clocks and human bodies through multiple time zones. The clocks record tiny distortions predicted by Einstein's theories. The bodies record the slow re-entrainment of hormones and alertness. Both sets of records tell a tale of resilience and adaptation. One records the universe's geometry, the other records how life tunes itself to that geometry. We have then at least three ways to encounter time: the private, felt time of attention and memory, the shared, regulated time of clocks and institutions, and the physical, structural time of the universe's geometry and thermodynamic history. The word we use for the last of these is often cosmological time, and it is the axis around which tonight's deeper questions turn. Cosmology asks about the beginning and the large-scale evolution of the universe, and in doing so, it confronts the puzzle of why time appears to have a direction at all. There are many reasons why this inquiry is gentle and also slightly discomforting. To talk of the universe's beginning is to talk about conditions when ordinary notions of space and time may not apply in any familiar sense. To ask whether time is fundamental or emergent is to ask whether the clock on your bedside table rests upon something more primitive, something from which both clocks and clocks of minds might arise. Physicists have proposed that time at the deepest level may not be a primary ingredient of reality, but a phenomenon that emerges when many microscopic pieces are counted together. Temperatures, after all, arise from an enormous number of particle motions. Perhaps time, too, is a kind of statistical confection. This is a theoretical idea. It is not a settled fact. It is a way of trying to bridge the chasm between quantum mechanics, which governs the tiny, and general relativity, which governs the large. One attempt in that direction uses an equation with a careful, peculiar name, the Wheeler-DeWitt equation, which describes wave functions of the universe. In some formulations, that wave function does not carry an explicit time parameter.
That absence has inspired suggestions that time, as we know it, might emerge from relations among entangled quantum parts, or from coarse-graining, very fine-grained structure into something that behaves like a flow. I mention these things not to confuse you, but to let you feel the scale of the problem. Different scientific languages describing reality arrive at a point where their dialects do not quite match. Bridging them requires imagination, care, and sometimes a radical rethinking of what the word time even means. There is no consensus. There are proposals, models, whispers of mathematical structures that sound promising. And there is always experiment, the steady companion that tells which ideas fall into line and which remain, for now, elegant fictions. We will return to those deep quantum puzzles. For the moment, though, keep with me in a quieter mood. Think of time as a companion with many faces, the face that sits with you in rush-hour impatience, the face that hangs heavy in the curve of a sundial's shadow, the face that a pendulum borrowed from the human impulse to swing can mimic, the patient face of an atomic clock that counts tens of billions of oscillations, and the elastic face that relativity allows when speed or gravity come into play. Each face is real in its context, each reveals some truth about the universe. Soon we will walk into the idea of entropy and the arrow of time, and how cosmology frames that as a question about the universe's initial condition, a question that has kept many brilliant minds both awake and gently bemused. For now, let the images settle. A shadow moving on a stone, a pendulum swinging in a quiet room, a tiny cesium atom cycling its energy states billions of times each second, and a massive star bending space like a fist pressed into a mattress. Hold those images as you breathe. They will serve as guideposts for the next part of our journey, where we will ask why things always seem to go from less disorder to more disorder, and why the universe might have begun in such an exquisitely ordered state. There is an intimacy to the question, because it connects your own experience of irreversible moments, a cup spilling, a memory forming, with the grand sweep of cosmic history. For now, rest in the idea that time wears many clothes, and that in each of them it is both stranger and more familiar than we first suppose. Now, let the images we have gathered, the sundial's shadow, the pendulum's arc, the cesium atom's steady pulse, the trampoline that sags beneath a heavy ball, settle into a quiet, companionable stack. We will lean on them as we move into the story that connects a broken glass on your kitchen floor to the enormous, luminous beginning of the universe itself. This is where the word entropy arrives, not as a cold technicality, but as a simple, intimate fact about how arrangements tend to change. Think of a glass falling from a table. It is an ordinary, gentle event. A clink, a splash of shards, a small scattered geometry on the floor. We can picture that fall forwards in time with no difficulty, intact, slipping, breaking, scattering. Now try to imagine the reverse as common sense. Every shard rising up, edges finding their way back into the bowl reassembling on the table and settling back into place. It feels absurd. It is not forbidden by the microscopic laws that govern particles. Those rules are largely time-symmetric, but on the macroscopic level we never see the reassembly. Why not? The common answer is entropy. Entropy is a measure of how many ways something can be arranged. An ordered bowl has relatively few ways to be arranged. A scattered pile of fragments has tremendously many. When you release a system, the most likely destination is the one that can be realized in the greatest number of ways. Over time, systems tend to move from less probable, more ordered states to more probable, more disordered ones. The second law of thermodynamics, stated simply, says that the total entropy of a closed system tends not to decrease. That statistical nudging is what gives us the arrow of time, a practical distinction between past and future. There are warm metaphors for this. Think of made and unmade beds. A smooth, tucked bed is one arrangement. Tossed sheets have far more possible configurations. A child leaping on the mattress will find many ways to rumple it. If you allow a system to evolve with no intervention, the number of possible microstates typically increases. Scrambled eggs are an everyday illustration. You can whisk eggs into a uniform mixture easily, but unscrambling them into their former discrete spheres is not something your kitchen will oblige. If entropy gives time its direction locally, cosmology asks a bigger question. Why did the universe begin in a state of such low entropy that allowed lots of increase thereafter? The early universe, as revealed by observations of the cosmic microwave background and theoretical reconstructions, seems to have been astonishingly smooth and ordered compared with what might have been expected. That low entropy starting point is what lets history unfold with dramatic gradients, galaxies forming, stars kindling, continents shifting, life arising. If the universe had begun in a chaotic, high-entropy state, there would be far less story to tell. Physicists have offered several ways to think about this initial order, and I will gently walk you through a couple of the more commonly discussed ideas, always with the invitation to treat them as hypotheses rather than final answers. One way is to accept the past hypothesis that the universe started in a remarkably special state and that this condition is a boundary condition of the cosmos, perhaps simply a brute fact to which we must make peace. Another idea invokes cosmic inflation, a period of extremely rapid expansion early on, which can take certain initial configurations and stretch them into large, relatively uniform regions, setting up conditions that look low in entropy for the subsequent evolution of structure. Inflation is attractive because it explains a number of features of the observed universe, but it does not by itself fully demystify why the initial patch had the right properties to inflate. There are more speculative and more exotic suggestions too, and here I must take care with tone, because speculative ideas can be tempting to present as certainty. Some researchers have explored scenarios in which the arrow of time might be local or even reversible under certain global conditions, or where the apparent arrow emerges from coarse-graining microscopic degrees of freedom into macroscopic phenomena. Others have proposed that what we call the past is simply the region of the universe that earlier had fewer microstates, and that other regions might have different arrows entirely. These are intriguing possibilities. They are also very much areas of active research. The best thing to hold as you listen is a sense of openness. The question of the universe's low-entropy beginning is one of those gentle but stubborn puzzles that keeps theoretical physicists both busy and delighted. If we step back a little, we can see how the arrow of time you feel in the world of coffee cups and car engines is tied through entropy to cosmic history. The directionality you sense when a memory settles into place or when an egg is scrambled is not merely psychological padding. It is aligned with the thermodynamic bookkeeping of an evolving cosmos. That alignment is a remarkable stitch between the large and the small, a cord that ties your personal narrative to the universe's. And yet, when we move to the realm of the very small, the quantum world, time begins to play a subtler game. In ordinary quantum mechanics, the Schrödinger equation provides a rule for how a system's wave function evolves. Time appears there as a parameter, a coordinate against which the wave function changes. But when physicists try to combine the quantum description of matter with general relativity's description of space-time, complications appear. One particular formulation that fits into the landscape of quantum gravity attempts is represented by an equation bearing the names John Wheeler and Bryce DeWitt, the Wheeler-DeWitt equation. In some incarnations, that equation does not include time in the way we are used to. It treats the universe's wave function in a manner that looks timeless. That absence has led to a very fertile line of thought. Perhaps time is not a fundamental ingredient, but an emergent property that arises when we look at subsystems of the universe. To grasp this gently, imagine how temperature works. An individual molecule does not have a temperature. Temperature is a statistical property of a vast ensemble of particles. When many particles interact and share energy, we can assign a temperature to the collection. Might time be like that, a statistical, emergent quantity that appears when we coarse-grain a micro-world into a macro-world with histories and records? Julian Barber, whose name you may have heard in whispers, has argued for a timeless view, in which the universe is a collection of distinct configurations, each a complete way the universe could be. The sense of motion and flow arises from relations between these configurations, not from a background clock. Other researchers pursue ideas where entanglement between subsystems plays the role of knitting together a notion of time. Correlations grow, information flows, and with that growth, a sense of temporal ordering emerges. These proposals are elegant and provocative, and they invite us to think of time as a pattern rather than a primitive. I will add an important caution. None of these accounts is yet established in the way that, say, atomic clocks are established as precise devices. They are lively ideas, mathematical frameworks, and conceptual tools. They suggest different pathways by which our familiar, flowing time might be a macroscopic illusion built on a more intricate, perhaps more static foundation. If that sounds like philosophical theater, it is partly because the debate lives at the intersection of physics, philosophy, and mathematics. That intersection is a rich ground for slow, careful thought. One practical way that researchers check such ideas is to look for empirical footprints. Quantum gravity is difficult terrain for experiments, but clever strategies abound. Entanglement experiments, tabletop quantum optics, and cosmological observations all provide hints. Some physicists look at how decoherence, the process by which quantum possibilities appear to collapse into classical outcomes as systems interact with environments, can give rise to a preferred basis that defines records and histories. In that view, the growth of entropy and the workings of decoherence together help to explain why the classical world looks time-streamed and why memories record a particular direction. Let us pause for another small domestic metaphor. Picture a vast, very finely woven tapestry. Up close, you see threads crossing in an intricate, seemingly timeless pattern. Step back and you perceive a flowing scene, a river in motion, a narrative. The motion is not absent in the threads, rather it becomes legible at a different scale. Similarly, the microphysics might be static in certain formulations, but when one steps back, when one coarse grains and looks at correlations, entanglement, and statistical tendencies, a flow of time emerges for observers within the tapestry. As we fold that image away and bring forward a softer tone, we can return to the lives that the cosmic clock supports, organisms with cycles tuned to day and night. Biological time is a friendlier, immediate subject and deserves a gentle, careful walkthrough. The suprachiasmatic nucleus in the brain, the SCN, is often called the master clock. It is a tiny cluster of specialized cells that responds to light signals and orchestrates the body's daily rhythm. Melatonin, which you may have heard of, rises in the evening and signals a preparedness for sleep. Cortisol has its own morning rhythm. Body temperature follows a gentle waveform throughout the day. These rhythms are robust but also flexible. They entrain to external cues, sunlight, meal times, social rhythms. People vary in their chronotypes. Some are larks, waking early with an ease that feels like sun spilling into a room. Others are owls, coming alive at dusk when the rest of the world dips. These differences are partly genetic, partly shaped by environment and habit. They are ordinary variations in how biological systems align with the planet's cycle. When those alignments are disrupted, think jet lag, night shifts, or sudden changes in routine, the body responds with fatigue, a muddled sense of time, and a slow re-entrainment process. It is a humbling reminder that our inner clocks are not purely abstract. They are embodied, chemical, and delicate. There is poetry in noticing the coexistence of scales here. While cosmologists calculate the age of the universe in billions of years, your SCN ticks out cycles measured in hours. Both are timekeepers. Both are real in their domains. It is one of the quieter wonders of being a creature in a cosmos that supports both kinds of regularity. The psychological sense of time, which we visited earlier with flow and waiting rooms, comes back into view as we think about aging and memory. As we age, many people report the decades seem to shrink, that summers of childhood expand in recollection, that the map of personal history becomes a compressed image. This sensation is partly cognitive. Novelty lays down denser memory traces, and routine lays down sparser ones, and partly social. The responsibilities and habits of adult life often reduce the number of firsts we encounter. Rituals and deliberate attentional shifts can create new bookmarks, new textures that slow perceived time by increasing the richness of memory encoding. There is a gentle experiment you can perform in your mind when you wish to cultivate a sense of expanded time. Notice 3 small things you have not noticed before in your immediate environment. It might be the particular pattern of grain in a wooden table, the way light hits a lampshade, or the specific sound a kettle makes as it reaches its boil. Those small attentional habits are not magic. They are practical habits that increase novelty and therefore the brain's opportunity to encode experience richly. The result is that, on reflection, your days feel fuller. In that way, you exercise a kind of psychological stewardship over how you experience time. Another human response to time's flow is storytelling. Memories are not mere lists, they are stories we assemble to make sense of sequences. A photo album is a wonderful metaphor here. Each photograph is a still, a frozen slice of the past, and when we page through, we stitch them into narratives. In the block universe philosophical picture, which we will touch on in a moment, the album is taken rather literally. All photographs exist, layered in space-time, and our consciousness moves through them like a finger along glossy pages. Whether one finds that comforting or unsettling is a personal note. I find it oddly soothing. It offers a way to think about continuity without insisting the present is a metaphysical spotlight that wipes out the rest. Now, for a gentle turn into the realm of imagination, time travel, as a concept, invites both delight and caution. There are experimentally verified ways to travel into the future relative to other observers. Time dilation under special relativity is not a magical fiction. It is an experimentally confirmed reality. Particles accelerated to high speeds in laboratory rings live slightly longer in the lab frame than they would at rest. Their decay clocks tick differently. Astronauts in low Earth orbit experience tiny differences in elapsed time compared with people on Earth. These are modest and practical variants on the theme of time's relativity, and they have been measured. When writers and filmmakers take the step of sending a character back into the past, they step into territory that is speculative and constrained. Certain solutions to Einstein's equations admit structures called closed time-like curves, which mathematically allow world lines that loop back in time. Wormholes, theoretical tunnels through space-time, are sometimes invoked as devices that could, under very particular and, as far as we know, physically non-trivial circumstances, permit connections between widely separated regions of space-time that might be interpreted as shortcuts in time as well as space. I must stress, these are speculative constructs that require exotic conditions, such as negative energy densities or forms of matter we have not observed. They remain an area of theoretical exploration rather than practical engineering. Speculative does not mean frivolous. Physicists use thought experiments to probe consistency. One famous issue is the so-called grandfather paradox. If you could travel back and prevent your grandfather from meeting your grandmother, how could you then have existed to travel back in the first place? Various proposals have been floated to resolve such paradoxes. The Novikov self-consistency principle suggests that only self-consistent histories can occur. Actions in the past that would lead to contradictions are forbidden by the laws of physics. Another route is to invoke branching worlds, in which each act of retro-causal influence spawns a new branch, a new world history. That idea borrows from interpretations of quantum mechanics and remains speculative. A peaceful philosophical alternative is the block universe picture, or eternalist view, where past, present, and future coexist tensely, and changing the past is not meaningful because all events are already part of the four-dimensional tapestry. The important point for our slow and reflective walk is this: some forms of time travel, specifically forward time travel via high-speed motion or gravity wells, are real and measured. Other forms, notably backward travel into a manipulable past, sit firmly in theoretical territory, with practical barriers that, at present, read as prohibitive. When people speak confidently of traveling back through time in the literal, causal sense, it is worth listening for the qualifiers. The story is richer and safer when one respects the boundaries between established physics and imaginative speculation. Philosophy, meanwhile, provides us with nourishing frameworks to hold these scientific possibilities. Presentism is the view that only present events are real. Under presentism, the past has ceased to be and the future has not yet been made. Eternalism, the block universe picture, treats past, present, and future as equally real. The flow of time on this view is a feature of consciousness moving along a pre-existing manifold. Both frameworks carry psychological consequences. Presentism maps neatly onto our felt sense of immediacy, but it strains to accommodate relativity's lack of a universal now. Eternalism aligns more comfortably with relativistic space-time, where slices of simultaneity are relative to observers, but it can feel counterintuitive if you value the reality of change. There is also the pragmatic middle way, time as emergent. Even if the fundamental equations of a future theory do not include time explicitly, the emergence of a thermodynamic arrow, decoherent histories, and the robustness of memory may together provide the scaffolding that lets beings like us talk coherently about past and future. The photo album metaphor returns here with a calmer voice. Whether the album is pre-laid or being made page by page might be less important than the fact that we can turn the pages and experience continuity. That experience is real, and it matters to how we live. At this stage of our exploration, you may notice a feeling of small astonishment. how a single word, time, picks up so many weights. It is a psychological companion, a biological metronome, a social coordinator, a property measured by metal and radiation, a variable in equations that curve space-time, a statistical tendency governed by entropy, and perhaps an emergent pattern of quantum relations. None of these claims cancels the others. Instead, they form a layered portrait in which each layer is intelligible at its own scale and in its own language. As we come to the closing passages of this walk, I invite you to bring these layers together in a personal image. Imagine your life as a window on a long, varying landscape. Close by, in the immediate yard, the flowers follow a day's rhythm, opening and closing like the hands of your biological clock. Farther out in the city beyond, a network of clocks coordinate trains and calls. Their mechanical and electronic pulses make the pulse of civic life. Beyond the city, the curvature of space-time bows subtly around mountains and masses, imperceptible to your senses, but recorded carefully in atomic clocks. And deeper still, stretched much further than any eye can see, the history of the cosmos unfolds in a sweep set by an initial condition that allowed complexity to arise at all. Each perspective is true in its domain. Each perspective speaks of different scales of order and different ways of measuring and experiencing duration. There is a particular solace in that multiplicity. If you are lying in bed, noticing the soft background tick and the rhythm of your breath, you are not distanced from the cosmos by the grandeur of its scales. You are nested within them. The very fact that atoms provide a reliable beat for your devices, that relativity must be accounted for in the maps on your phone, that entropy provides direction to your memories, and that your circadian rhythm coexists with all of this, these are not contradictions. They are a kind of multi-layered choreography in which you participate.
Before we close, allow me one gentle practical invitation. If any part of this slow voyage through time resonated, if you felt the small delight of seeing a familiar day reframed, or the mild exhilaration of picturing space-time as a mattress bowed by a star, a small click of like and a quiet subscribe helps this restful corner find others who might appreciate it. No hurry, only if it feels right. Now, in the very last few minutes of our shared attention, I will offer a brief calming synthesis, and then leave the image of now as a soft landing. The true nature of time in the universe, as we have seen, is not a single simple thing. It is a family of related concepts. It is the mind's way of weighing moments and filing memories. It is the body's chemistry aligning to day and night. It is the machinery of gears and quartz and atoms making practical agreements for coordinated life. It is the shape of space-time that bends clocks and light. It is the statistical tendency for arrangements to gravitate toward greater multiplicity, which gives us an arrow. And it is, perhaps, an emergent pattern that arises when the universe's fundamental ingredients are viewed in the round. Hold that list not as a parcel of competing truths, but as a chorus singing the same tune in different keys. Each voice adds timbre, and together they form a lullaby for someone who is ready to rest. If your thought is heavy with questions, whether time is fundamental, whether the universe's beginning had to be the way it was, whether past travel could ever exist, know that those questions are both the point of science and the comfort of human curiosity. They keep the mind gently lit like a bedside lamp whose glow is not intended to banish sleep, but to guide it. As you prepare to disrobe from the day's concerns,
Picture again the images that have kindly accompanied us, the shadow moving across a sun-warmed stone, the pendulum's slow metronomic swing, the tiny patient oscillation of a cesium atom counted 9,192,631,770 times in a single second, the trampoline sagging under a heavy mass, the mattress cupped by a star's gravity, a photograph album whose pages you can turn with soft fingers. Let them fold into one another like soft linens. You are, in this present moment, both anchored and afloat. Your now has weight and softness. It connects you to a human history of clocks and to a cosmic history written in light. There is no need to resolve all mysteries tonight. It is enough to rest in the company of wonder, to let questions be gentle companions rather than urgent tasks. If you close your eyes now, you carry with you not only the idea of time's mysteries, but the quieter lesson that you can shape some of your time by attention, by small acts of novelty, by soft rituals. If you choose to sleep, the world will keep its manifold rhythms around you. The atoms will keep their cycles. The pendulums will continue their arcs in other rooms. Satellites will whisper timing signals high above, and the universe will slip along its long, slow history. You, tucked into the present, are a small and wonderful part of that story. If you would like to come back and wander through these ideas again, to hear the slow weave of cosmology and bedtime thought, a gentle subscription helps build a little library of restful explorations. And if there is someone you think would enjoy this quiet voyage, sharing it is the kindest way to invite them along. Rest now. Let the questions drift like dust motes in late light, and let the steady rhythms, inner breath and outer tick, be the soft rails that carry you toward sleep. Good night, and may your hours be kind.